Bismillahirrahmanirrahim. Assalamu alaikum, students. Today, I will start with solving a simple problem. Actually, I have to establish a result in thermodynamics, and to establish that result, we will first solve a problem that will help us to understand the result to be established by us together in this lecture. So sample problem goes like this. The problem says 2 mole of an ideal gas undergoes isothermal expansion along 3 different paths. Along 3 different paths. First, reversible expansion from Ti equal to 25 bar is a unit of pressure, remember, and Vi equal to 4.5 liter. Liter is a unit of volume. To PF equal to 4.5 bar. Second, a single step expansion against a constant external pressure of 4.5 bar, and third one, let us use another color. A two-step expansion consisting initially of an expansion against a constant external pressure of 11 bar until P equal to P external followed by an expansion against a constant external pressure of 4.5 bar until P is equal to P external. Calculate the work for each of these processes. Second part of the question says, for which of the irreversible processes is the magnitude of the work greater? Let me repeat the problem. Problem goes like this. 2 mole of an ideal gas undergoes isothermal expansion along 3 different paths. First one, reversible expansion from Pi equal to 25 bar and Vi equal to 4.5 liters to Pf equal to 4.5 bar. Second, a single step expansion against a constant external pressure of 4.5 bar. And third one, a two-step expansion consisting initially of an expansion against a constant external pressure of 11 bar until P is equal to P external followed by an expansion against a constant external pressure of 4.5 bar until P is equal to P external, right? Calculate the work for each of these processes, for which of the irreversible processes is the magnitude of the work greater. So let us move to the solution. First, understand the question. I want to highlight certain things first. So our system is an ideal gas. Let me use this color. Our system is an ideal gas. What is the amount? We have 2 mole of an ideal gas, right? Now this undergoes isothermal expansion. That means the gas expands, its volume increases, and during the expansion, temperature stays constant because process is isothermal, right? Now, this ideal gas undergoes isothermal expansion along 3 different paths. That means in 3 manners. In first one, it follows a reversible expansion from Pi equal to 25 bar, Vi equal to 4.5 liters. That means Pi and Vi are its initial pressure and volume. It goes to the final pressure 4.5 bar, right? And in second situation, it undergoes a single step expansion against a constant external pressure of 4.5 bar. And this question indicates that this gas is externally exposed to a constant pressure of 4.5 bar. That means process is externally done by 4.5 bar pressure. Then another is a single two-step expansion. First, it initially expands against a constant external pressure of 11 bar until it attains 11 bar pressure. Then it is followed by another expansion against a constant external pressure of 4.5 bar until gas pressure becomes external pressure. P stands for here gas pressure. P external is the external pressure. Now we are supposed to calculate the work for each of these processes, 3 paths. And second thing, we have to check for which of the irreversible processes, second and third one is irreversible process, we have to check for which of these irreversible processes is the magnitude of work greater, right? So let us follow the solution. We first need to calculate the constant temperature at which the process is carried out. Let us calculate that. We first calculate the constant temperature at which the process is carried out. So we calculate that. Right? So how we can find that? Using ideal gas equation. You know ideal gas equation PV is nRT. I can write T equaled PI VI by nR. I know initial pressure, initial volume, number of moles, universal gas constant. So I put the values. Let me use some other color. My initial pressure, remember, is 25 bar. It is 25 bar. My initial volume is 4.5 liter. This is 4.5 liters. So I put that value. Then N is 2 mole. Then I have to put the value of R, which is 8.314 into 10 raised power minus 2 liter R per mole per Kelvin. We are using the suitable units for R. So value of R is 8.314 into 10 raised power minus 2 liter bar per mole per Kelvin. So when you solve for T, you can check it. We get 677 Kelvin. That's our first step. We know now that the process is carried at constant temperature of 677 Kelvin. Now another thing, if you see the data doesn't give us the final volume. So we want to find that. So next, we calculate the final volume. So next we calculate the final volume. Again, we use the ideal gas equation. It will be nRT by PF, because PF will be equal to nRT. There is no T is constant, so Ti is same as Tf is same as T, which we have solved, right? So Vf is nRT by Pf. So let us solve it. Substitute the values. N is 2 mole. Then we have R 8.314 into 10 raised power minus 2 liter bar per mole per Kelvin. Liter bar per mole per Kelvin. And we multiply it by the temperature. We'll solve that, which is, let me use another color, into, what is the temperature? 677 Kelvin. So this is our numerator. Right? N, R, and T we have substituted. And downstairs we have final pressure, which is given as 4.5 bar. This is given here, 4.5 bar. We substituted all the values. Now we solve for Vf. When you solve for it, you will get 25 liters. Another quantity we have found, the final volume of the gas is 25 liters, right? Now we have to calculate another thing. Which another thing? First, I will draw the diagram, or I will tell you. See, uh, in single step expansion, we know the initial volume is 4.5 liters, and it directly goes to the final state in which the volume is, which we have solved for 25 liters. So for this step, we know initial volume and final volume. But in third path, we have a two-step expansion. First, expansion goes against the constant external pressure of 11 bar until P is P external, followed by the expansion against constant external pressure of 4.5 bar. So at 4.5 bar pressure, we know the volume, but we want to find the volume of this gas for this two-step expansion at 11 bar pressure. That means intermediate volume, right? So if we find that. Next, we calculate the intermediate volume in the two-step expansion, right? Calculate the intermediate volume in the two-step expansion, that is third part. So we call that V intermediate, V int, which will be equal to nRT by P, intermediate pressure, which is 11 bar, as we have discussed. Let us substitute the values again. Let me use another color. N is 2 mole. Then we have 8.314 into 10 raised to minus 2 liter bar. So I don't have space here, so I will do something. I'll write it another way. Make this little bit tilted line. Now I substitute the values. So I have, actually numerator is same as this VF. That is 2 mole, and I will reduce the font. 2 mole times 8.314 into 10 raised to minus 2 liter bar per mole per Kelvin. This NR, then you have multiplied by temperature, 677 Kelvin. Then you have to divide by the intermediate pressure, which is 11 bar, right? 2 mole times 8.314 into 10 raised to minus 2 liter bar per mole per Kelvin times 677 Kelvin divided by the intermediate pressure, which is 11 bar. When you solve for it, you will get 10.2. Let me make it clear. 10.2 liter. We have calculated the intermediate volume as 10.2 liter. I will encircle it. Third thing we have found, right? Now I know the volumes, final volume, initial pressure, final pressure, and intermediate volume, intermediate pressure. So I can show this on a PV diagram. So let me draw a PV diagram. So this is my volume axis. It is in liters. This is my pressure axis, which is in the unit of bar. 25, let me, that's 0, this is 5, this is 10, this is 50, 20, 25, right? On this side, I have also 25, but I have small scale, the shorten the scale, 5, small space, 5, 10, 15, 20, 25, right? So where we start? What's our PI and VI? First, I will make an approximate figure. So what's my PI and VI? My PI is 25 bar and VI is 4.5 liter. 4.5 liter, 25 bar. So 4.5 liter is somewhere here. Let me use another color. 4.5 liter is somewhere here. And 25 bar is here. So my point is approximately here, right? Then what is my final pressure and volume? 4.5 bar is external pressure. You can see 4.5 bar, this one. And final volume is 25 liters. It's 25 liter. On this side, you have 4.5 bar, approximately here. So we are here. This is my final point, right? So first I have this reversible path. Remember, it is an isotherm. So this is my path 1, right? Which is reversible. Right? We are going from Initial pressure 25 bar, 4.5 liter initial volume to 25 liter final volume and 4.5 bar final pressure, right? What's my part 2? This is my part 2. I will use some color to highlight it. This is my part 2. This is my part 2. It's irreversible, right? Now, and we are moving from this point. Let me label this point. This is just drop it. You get confused. Where is my eraser? Eraser. This is my eraser. To drop only this much. Let me get my pen back. Let me get my pen back. I want my pen. Let me fix it. Okay. It was like this. So we were here. This is my part 2. Right? And this part 2 is irreversible. Right? Because the process is not quasi-static, it's irreversible. What is my third bath? Remember, in bath third, first we have pressure of 11 bar. Because we expand first at 11 bar until pressure is we expand at 11 bar pressure. So 11 bar is here approximately. Let me use some other color. It's 11 bar. I'm here. So I have 11 bar pressure until my volume is 10.2 liter. Remember the intermediate volume approximately here. So it is up to this point. So this is my first step in part 3. Then when I reach 10.2 volume, then I expand along this path. Then my path coincides with this. Remember, there should be some redness in it, otherwise it will confuse, right? Now this green one is my path 3. First, the expansion takes place at 11 bar pressure until volume is 10.2 liters. Then it takes place at the pressure of 4.5 bar, right? Let us move to the calculation of work. So this is our figure, right? Let us move. Next, we calculate the work. Remember, for isothermal expansion, work done by the gas is given by the expression nRT, natural logarithm of V2 by V1, where V2 is the final volume, V1 is the initial volume. We have derived it. So for path 1, which is reversible isothermal expansion, our work is nRT natural logarithm of V2 by V1. Now we replace the symbol. I write here Vf by Vi, because V2 is the final volume and Vi is the initial volume. So let us substitute the values. 2 mole times the value of R, 8.314. I will write now it in joules because I want work in joules. So I will express R in joule per mole per Kelvin, which is 8.314 joule per mole per Kelvin, right? 2 mole times 8.314 joule per mole per Kelvin times the value of temperature, which is 677 Kelvin, times natural logarithm of Vf, which is 25 liters, divided by initial volume, which is 4.5 liters. So when you solve for it, you will get 19.3 into 10 raised power 3 joule. So we have calculated the work for path 1, reversible path. Remember, we are using the convention for the work done by the gas as positive, work done on the gas as negative. And we have already clarified some books to the reverse. So our work is 19.3 into 10 raised power 3 joule, right? For path 1. Now, for path 2, which is single step process. Remember, in the figure, my path 2 is single step process. Process is taking place at constant pressure. So what is the work? W, I write it single. It stands for work done in the single step process. It is simply the external, because the process takes place at external pressure times the change in volume. External pressure is 4.5 bar times the change in volume. We convert first it into pascals in order to get our work in joules. So I multiply it by 10 raised to the power 5 Pascal over bar. Then I multiply by the change in volume. Remember the final volume is 25 liter minus initial volume is 4.5 liter, right? 4.5 liter is the initial volume. Then I convert this liter into cubic meter and multiply it by 10 raised power minus 3 cubic meter over liter. So remember, work done at constant pressure is just pressure times the change in volume. So it's P external times delta V, which is 4.5 bar times 10 raised power 5 Pascal over bar in order to convert the unit. Then multiplied by 25 liter minus 4.5 liter. Then there is a conversion factor 10 raised power minus 3 cubic meter by liter. So when you solve for it, you will get your answer as 9.23 into 10 raised power 3 joule. So this is the work done by the gas in this single step expansion R2, 9.23 into 10 raised power 3 joule. Now let us calculate the work for path 3. For path 3, which is two-step process. Let me use another color. So W, two-step. So we have to find work. Remember two-step process. This one, first expansion takes place at this pressure. Then expansion takes place at this pressure. Here volume, final volume is 25 liter, initial is 10.2. Here 10.2 is final and initial is 4. It was the initial pressure, initial volume is 4.5 liters, right? So we have to first find simple for work done for first portion, then add work done by the gas for the next portion and add two terms, right? So two-step is simply formula will be same, P external times the delta V, but in first step, P external is 11 bar. In second step, P external is 4.5 bar. So my solution is this. 11 bar times, which is the pressure in first portion of the path. Then I convert it 10 raised to 5 Pascal over bar times my final volume in first portion of the path 10.2 liters minus initial volume 4.5 liter. Then there is conversion factor times 10 raised to minus 3 cubic meter over liter plus work done for second portion of the path, which takes place at constant pressure of 4.5 bar. So I write 4.5 bar multiplied by the conversion factor 10 raised to 5 Pascal over bar times the difference in the volumes. My final volume is 25 liter now minus 10.2 liter times the conversion factor 10 raised to minus 3 cubic meter by L. I check the values. 11 bar times 10 raised by 5 Pascal by bar. Conversion factor times difference in volume for the first portion of the path, 10.2 liter minus 4.5 liter, times the conversion factor. Then I have second piece of the path. The work done for that piece is 4.5 bar times 10 raised by 5 Pascal over bar. Conversion factor times the difference in volume, 25 liter minus 10.2 liter, times the conversion factor. So when I calculate it, you can check it. It turns out to be 12.9 times the 10 raised by 3 joule. This W to step. Right? So this is work done for path 3. This work done for path 2, single step, and for path 1, which is reversible. So it is reversible path. This is irreversible. This is also irreversible. So what is the conclusion? Conclusion is the magnitude of the work is greater for the two-step process. The magnitude of the work is greater for the two-step process than for the single step process, but less than that for the reversible process. I repeat, the magnitude of the work is greater for the two-step process than for the single-step process, but less than that for the reversible process. Among the three values of work, you can see it is 19.3, the multiplier is same. It is 9.23, it is 12.9. So biggest value, largest value is reversible work. So reversible work is the largest. Among the two irreversible works, two-step process work is larger. Both are smaller than the reversible work, right? With this in mind, you keep this in mind that by reversible work is larger than both the irreversible paths, but when we compare the work done by the gas in these two reversible paths, by increasing the steps, work becomes larger, right? This all for today. We have to generalize this idea in next lecture. This all for today. Don't waste your time. Prepare your exams, and don't forget to subscribe my channel. Thank you. God bless you. Assalamu alaikum.